So how exactly do Minecraft shaders add shadows? And how do they make different materials react differently to light? Last episode, we coded a shader with distant horizon support and got it rendering just like vanilla does. Now it's time to implement custom lighting. We'll go through adding directional lighting, realistic material lighting with resource pack support, and shadows. Quick note on the Visual Studio Code extensions I've been using. Turns out I had this one disabled and that seemed to work better. Now it's time to finally one-up Minecraft's lighting. As you can see in traditional Minecraft, whether the sun is there or whether the sun is there, this side is still darker than this side and this side. So let's change that. In our basic frag.glsl, the first thing we need to do is get the normals. The normal is just a direction. Pretend that's a cube that points out of a surface. Tells us which direction a surface is facing. The way you can get a normal is in vec3 va normal. Now each vertex has a normal. That's why we're running this on the vertex shader, but for each triangle, these normals are interpolated and then it'll be pointing up out of the surface. And that is exactly what we want. So let's do in vec3 va normal. Let's do geonormal. I'll talk about what a non-geonormal is soon, but that just stands for geometry normal. And this is because it's a normal of the geometry equals va normal. And let's make that an output. Geonormal. Now we're going to need to transform this normal into the correct space, and for that we can use the uniform mat3 normal matrix. Normal matrix times VA normal equals geonormal. In our basic frag, let's get this geonormal in, and just for a visualization, let's go ahead and display the geonormal. See what it looks like. And look at that, everything is all colorful. So what we're doing now is visualizing a direction with a color. And this can be kind of hard to conceptualize, but if we look at a surface, basically what we're doing is taking the X, Y, Z of the direction and visualizing that as RGB. So something that is more red has a bigger X than anything else. Something that is more green has a bigger Y than anything else. Something that is more blue has a bigger Z than anything else. Can you tell what space we're in just from the color? Our normals are right now in view space. That means it's blue when it's pointing at us, so that's the Z direction. It's red when it's pointing to the right, so that is the X direction. And it's green when it's pointing up, which is the Y direction. Now we'd like to convert this space from view space to world space. So let's consult our handy chart. We are in view space, we need to get to world space, and here is an interesting fact. Converting a direction in 3D space can be different than converting a point in 3D space. That's because when you multiply a matrix that has 4 terms, the 4th term helps change the position. So if we multiply, as here, by a mat3 version of a matrix, we're only changing the direction but not the position. This is because view space and player space have the same origin at the camera. However, if we're multiplying a matrix 4 with 4 terms by a vector 4, then we will also move the origin. A way we could do this conversion for a direction if we had the normal here for the view position is to just put a 0 instead of a 1 in the vector 4. Here we can take advantage of another fact. These 3 different spaces, world space, feet player space, and player space, all have the same directions. All they do is move the origin. World space centers it at the world origin, which is the coordinates 0, 0, 0 in your Minecraft world. Feet player space, which is actually a misnomer, has its origin at the camera or the head of the player. The only thing that player space adds is view bobbing. When you're walking and your head bobs up and down as you walk, player space moves the origin up and down with your head movement. But they all have the same X, Y, and Z direction, which is oriented to the world. You can see which way this points by using the F3 menu. It even says facing east towards positive X, facing south towards positive Z. The only thing it doesn't mention is that when you're facing up, you're facing towards positive Y. So to convert from view space to a world space direction, which is the same for all 3 of these, all we have to do is mat3 gbuffer model view inverse. So let's take our geonormal, vec3 world geonormal, and we will multiply this by a mat3 gbuffer model view inverse. We just have to define this, mat4 gbuffer model view inverse, and let's see these normals in world space. Well, before we do that, let's actually put the right normal in there. And there we go. It's pointing blue towards positive Z, red towards positive X, and green towards positive Y, no matter which way the player faces. Now let's do the same thing for distant horizons. Once again, distant horizons is using the older syntax, so instead of VA normal, this will be GL normal. Let's pass out a vec3 geo normal, set this equal to GL normal, and to transform this one into the right space, we can use the GL normal matrix. Let's pass in the vec3 geo normal, visualize the view space one first, and look at that. Just as expected, it changes as our camera moves. Then let's do that same conversion from view space to world space. We just need to make sure we pass in the uniform mat4 gbuffer model view inverse. And look at that. It all blends together. No matter where we move our camera, that side is red, up is green, and that way is blue. Beautiful! Now how do we translate these colors into some actual cool lighting? We can use the uniform shadow light position. So let's grab the shadow light position. What we can do to convert this position into a direction, vec3 shadow light direction, is simply normalize it. Normalizing takes a vector in any direction, let's say with length 2, and makes it so that it's in the same direction, but the length is 1. This is very useful for many calculations. Now that we have a shadow light direction, let's go ahead and start displaying the output color again. Remember that we have it set to the power of vec3 1/2.2 in distant horizons as well. Now that we have a shadow light direction and the direction that the surface is facing, we can create a float light brightness variable and have it be the dot product between the shadow light direction and the world geonormal. The dot product just tells us how much these two directions point in the same direction. If they point in the exact same direction, the dot product is 1. If they point in opposite directions, the dot product is -1. If they are perpendicular to each other, the dot product is 0. This is very useful to us because, say this is the sun and this is the normal of the block, you can see that if this is the surface of the block, the sun is going to hit it. However, if this is the normal of the block and the sun's going this direction, it's going to hit the other side of the block. It's not going to hit the block at all. Likewise, if they're perpendicular, the sun's not going to hit the block. It's going to miss, go right by. The only difference is that the sunlight will actually be reversed because it's a direction that points towards the sun, not the other way around. So if the surface points towards the sun, light from the sun can probably hit it. But if the surface points away from the sun, light from the surface probably can't hit it. To prevent negative values, if we just clamp this between 0 and 1, which just prevents it from going below 0 or above 1, here is a common element of confusion. Eye space is another name for view space. So if it says it's in eye space, it's actually in view space, not eye player space. Eye space and eye player space are very different. So we will need the sun to actually be in eye player space, so the direction will be in world space. So let's multiply by mat3 gbuffer model view inverse. Mat3 gbuffer model view inverse times shadow light position. And remember to normalize and then multiply this light brightness with our output color, and look at that. Now we have brighter surfaces if they're facing the sun, and darker surfaces if they're facing away from the sun. Of course, it wouldn't be pitch black if you're facing away from the sun. Light from the sun would bounce off other surfaces like the ground here and hit nearby objects. An easy way to simulate that is to just set a minimum light value. So let's clamp the light brightness between 0.1 and 1. And look at that. If you compare vanilla and our shader, we have dark surfaces, not just always on the same side, but on the sides that are not facing the sun. This surface is facing the sun, so it's the brightest. This one is sort of facing the sun, so it's less bright. And these ones are not facing the sun, so they're the darkest. To make things extra nice, we can try to match the ambient lighting to the darkest vanilla value. So let's make it 0.2. Looks like we have a little error here. We just need to make sure that this is specific specifically a float, a decimal value, because it'll be assigned to a float. That looks just about right. Let's set the tick rate to something ludicrous. And let's turn do daylight cycle on because I have it off for testing purposes. And as the sun dashes through the sky, we can see the brightest surface change, gradually blending from brighter on top to brighter on this side. Please ignore the very hyper chicken. We do have a bit of a flashing transition when the moon comes out, but other than that, it's easy to see the benefits. Now let's make sure that the distant horizons blocks are also shaded in the same way. We can just copy and paste this code. We'll do something a little fancier with include directives a bit later. We already had the world geonormal, so let's delete the original. And we just gotta grab the shadow light position. And finally, before the fog blend value, so that we don't have strange shading artifacts in the fog, let's take the output color and multiply it by the light brightness. Get ready for something beautiful. Look at that, we have shading! And not only shading, it's the same shading in distant horizons as is in normal vanilla blocks. It all blends in together. You'll also notice that this shading applies in real time to entities and what you're holding. Since we started with everything vanilla, here's something really cool. Even something we haven't even looked at, like the nether, is entirely functional. It looks pretty much the same as vanilla. I can't even tell when my shaders are enabled or disabled. In the nether, there's no sun or moon, so all the light is from block light. That's why we're seeing literally no difference yet. Our next step is going to be adding support for texture packs. The steps that we're going to follow will work with any labPBR resource pack. I will be using Weed Eater. I always forget to include Minecraft in this, which recently had an update. Grab the labPBR version. If you do want to go with this one as well, make sure to check out my tutorial on how to install it. As well as the file you download online, you will need a pack.zip file, which you can generate using my tutorial. Put both Weed Eater and pack.zip in selected. If you chose a resource pack that has different colored textures, then you'll see them right away. But for the texture pack that I chose, that only adds normals, everything still looks the same. So let's work on adding texture pack normals. In our basic frag, let's add uniform sampler 2D normals. Let's get our vec3 normal from sampling this texture. Normals with our text chord. Now, the reason that I will name this normal data instead of normal is because in labPBR, the normals are encoded into only the X and Y channels. On the Shader Labs website, under labPBR, we can see why this is. The third component can be reconstructed using this equation. So let's use it. Vec3 normal equals that equation for the Z component, and for the XY component, we just use normal data.xy, and I accidentally put normal instead of normal data there. Since this is a texture, it will be in the range between 0 and 1, and we want our normals to be in the range between -1 and 1. That's why we multiply by 2 and subtract 1. Now the space that these normals is in is a space called normal space, and it is not on our chart, but it's a space that's relative to the geonormal. There isn't a built-in matrix to convert a normal from normal space, so we'll have to construct one. This will be a mat3, and we're going to name it TBN. That stands for tangent, bitangent, and normal. If we look at a surface, the geonormal will be the direction pointing directly out of the face that we've already used. The tangent will be a vector that points along the face, and the bitangent will be another vector that points along the face that is perpendicular to both the geonormal and the tangent. We can use these three directions to convert a normal that's in normal space into world space. Again, in shader tricks, there is a function that creates the matrix for us. Let's copy and paste this, and for this function, we will need to input the geonormal and the tangent. Let's make sure that we're calculating the geonormal before this. Now the tangent is something we need to get on the vertex stage. The tangent is stored in invec4 at tangent. So let's go ahead and grab that and make another out value, tangent. Then we can just say tangent equals at tangent. Let's make that an in. Now we will have a TBN, and all we got to do is multiply that by the normal. To make this clear, I will call this the normal space, and this will be the normal in world space. Let's make sure this is the geonormal in world space. And we will only need the R, G, and B of the tangent. And let's make sure to declare this One last thing we will need to do is make sure the tangent is also in world space. So let's copy this world tangent and put the tangent right here. .xyz, and the world tangent is what we'll put into there. The light brightness calculation is what takes the normal into account, and right now it's still using the geonormal. So let's grab the normal world space, put that into the calculations, and we have normals. Something's not quite right though. These blocks that are right next to each other should look the same, but they don't quite look the same. We can, however, see they don't change as we move, which is a good sign that we're in the correct space. Here we see for DirectX normal mapping, you want to switch the order of these. And labPBR, which we're using now, uses DirectX style mapping. The normal vector should be encoded in the DirectX format. So we need to do cross tangent normal. So let's switch the tangent and the normal here. Now that didn't fix it, but this will. Before we do this calculation here, that finds the z coordinate from the x and the y coordinates, we need to make sure our normal is between -1 and 1. And there we go, we have normals. For this one, we don't need to do anything for distant horizons because distant horizons doesn't have textures. Even entities that have normals will work. However, block entities seem to be having some sort of issue here, and that's because we forgot to do something. We simply forgot to multiply the tangent by the normal matrix. Since the tangent is a vector 4, we will need to do attangent.a and wrap this in a vector 4. Multiply the RGB by the normal matrix and keep attangent.a the same. Another thing we haven't done is we haven't made absolutely certain that tangent was normalized. And there we go. That was our issue. I don't know why it wasn't already normalized, but it is now. Absolutely perfect. When we compare our shader now to vanilla, we're starting to see some big differences. Also, something you may have noticed is we really haven't needed to have a separate terrain because basic and terrain are exactly the same and have been for a little while. From the Optifine documentation, we can see that gbuffer's terrain falls back to textured lit, and textured lit falls back to textured, and textured falls back to basic. So if we just don't include gbuffer's terrain, it will just run the code that's in basic instead, which is the same, so it won't change anything at this point. And look at that, we just made our code more simple. Let's do a little organization here. Let's group our sampler uniforms together. Uniforms, and these are our matrices, and these are our values. These are our outputs, and let's put our inputs above our outputs. These are our vertex to fragment values. This is our output, and these are our functions, which is just one. Here we have our attributes that are sent in. We have here chunk offset is not a matrix, so we'll put that at the bottom as matrix. The matrices first, then the values, and here are the outputs, and there we go. Do the same here, put the inputs before the outputs, and functions. That's much neater. Let's put our color before any blendings. This is the distant horizons blend section. The output is pretty clear. And this part is our lighting calculations. And at the very top, let's put where we get the color. Get the base color. Let's set the output color first to just be the foliage color and not include the light color. We'll add that later because that's part of lighting calculations. Do times light brightness times light color. Nothing will have changed. And this part is already pretty darn neat. Let's put this together, view space position. Do the same thing for distant horizons. At the top, let's put our basic color. After light color, let's do output color times equals light color. These will be our lighting calculations. This is our depth testing, unique to distant horizons. And this is our distant horizons blending. Let's move this part up here, times the brightness and times the light color. And this is the fog blend, which will occur after the distant horizons blend. And there we go. Absolutely beautiful. Next, it's time to add some specular. Specular effects are what make shiny things look shiny when light kind of glints off of an object. Specular values are going to be stored in uniform sampler 2D specular, and we will be able to access that in the same way, specular and texture coordinate. In labPBR, we'll see the red channel is the smoothness, which is the main thing we're going to use right now, and it can be converted to linear roughness with this equation here. Let's go ahead and store a float roughness, and for perceptual smoothness, let's have that be specular data.r, red channel, and this is a float. Now we have roughness. This diagram really shows what specular highlights are. The ambient is just like our minimum light value. The diffuse is just like the light intensity value that we calculate based on the direction of the sun. And specular will add these little highlights, depending on how smooth the surface is. This is the equation that we will use. I know this looks really complicated, but I'm going to write it out so it's a little simpler. This means it's the sum over every light. So it goes for each light, it calculates this. We only have one light that we know where it is, which is the sun, so we're going to only do this once for the sun. This is our minimum light value, which we have accounted for in our lamp function, so we won't have to worry about that. KD and KS, we're just going to ignore for now. So what we have here is the dot product of the light direction and the normal. That is what we have right here, the dot product of the light direction and the normal. What we're going to add is R dot V, where R is the direction of a perfectly reflected ray of light, and V is the direction of the viewer. Alpha will be the shininess. KD and KS are what we're going to get from the roughness. The rougher a surface, the more it will be influenced by this term, and the smoother a surface, the more it will be influenced by this term. And we won't need to worry about the I terms. Our first step will be to find the reflection direction and the view direction. This is our surface, this is our light, and this is the point that we're going to be calculating. This is our light direction. This is our viewer. Little camera there. So this will be our view direction. Now the reflection direction will be the direction of the light. Just imagine that the light is going this way along this direction, and then it is reflected perfectly around the normal. Our view direction is pretty close to it, so it'll be about here. And this is our reflection direction, such that this angle and this angle are exactly the same. So let's calculate the reflection direction. Fortunately, GLSL has a handy little function called reflect. So to get our vec3 reflection direction, we just have to reflect the light direction around the normal. Oh yeah, I didn't actually call it normal, called it normal world space. Now we have a reflection direction. Next, we need a view direction, points towards the viewer. To find this, we'll need to take the camera position, so this position here, and subtract it from the position of the fragment that we're rendering. And if we normalize that, that will give us a nice view direction. So let's do camera position minus frag world space and normalize that. Now we need to define the camera position uniform, and we need to find the fragment in world space. You might remember we already have the view space position passed from the vertex shader. So let's start there. View space position to world space. First thing we need to do is multiply the G buffer model view inverse by the view position in a vector 4. So vec3, the frag in feet player space, equals the G buffer model view inverse times vector 4 view space position 1.0, because it is a position, not a direction. And then we just convert this to a vec3. And very simply, we just add the camera position. So vec3 frag world space equals frag feet player space plus the camera position. Now we have a view direction and a reflection direction. So now we need to calculate our KD and KS. KD and KS summed together will equal 1 because they are the amount of light that reflects off a surface. Part of that light is reflected as diffuse light, and part of that light is reflected as specular light. That's why together they equal 1. So KD, or the part of the light that will be diffuse, will be equal to our roughness, and KS will be equal to our smoothness. Not our perceptual smoothness, but a linear smoothness, which is simply the inverse of roughness. Then KD plus KS equal 1. Now we can go ahead and take the light brightness that we have right now. Let's rename this to diffuse light. Let's create a new float, which will be specular light. This diffuse light will be multiplied by the roughness, and the specular light will be multiplied by the smoothness. Here we have the light dotted with the normal, but here we will have the reflected direction dotted with the view direction. Reflection direction dot view direction. And then the light brightness will simply be the diffuse plus the specular. To make things a little more clear, let's make another one for ambient light and simply have this equal to 0.2, what we have right now as our minimum. Change that to 0 because we're now accounting for it here. Now we have light brightness equals ambient light plus diffuse light plus specular light. And something went very wrong. We have to remember that we're reflecting the light coming from the sun, not the direction of the sun. So we have to make this negative. And that is slightly better. I mean, it's coming from the direction of the sun, but everything should not be black here. The issue here is we're getting a negative value sometimes. So once again, we need to clamp between 0.0 and 1.0. Now, look at that. And right now, the effect is pretty subtle, but it is there for sure. To make the effect more pronounced, we can increase the shininess factor. What we do is set this dot product to a power. Let's do 100 to start out. Now we can clearly see the specular highlights. And even better, we can see the sun on the surface of the ocean. Notice there's very slight specular highlights for a rough surface like stone, and much brighter specular highlights for a smooth surface like iron. Beautiful specular highlights. Another thing we can do is scale this shininess factor by the roughness. Let's call this the shininess factor. Float shininess to smoothness times 100 plus 1. Now when smoothness is 1, very smooth surface, it'll be 101. But if smoothness is 0, it'll be 1. The rougher the surface, the more spread out the highlight is. You can also make this 200 if you want sharper highlights, or even 1000. Now the sun just makes a very small dot on reflective surfaces, but I think 100 is a pretty good value to go with. Now metals look a lot more like metal, but if you want them to look even better, there is a much more complicated specular equation called Cook-Torrance. I won't go into the details here, but I will show you my implementation. For this more complex specular function, we will need some more data from the specular texture. The reflectance is going to be stored in specular data.g. The reflectance is the minimum amount of light that can be reflected from a material. In labPBR, however, reflectance also stores whether or not something is a metal. You can have different values encoded for different metals, but we'll just use it as a binary, is this a metal? So let's create a float called metallic, set it to 0 for not being a metal, and let's create a vec3 called reflectance, which stores the reflectance of the material. Now, if the specular data.g times 255 is greater than 229, which is the cap on when there is reflectance, we know it is a metal, so metallic equals 1.0, and the reflectance can easily be approximated with the color of the actual material, which is what output color is right now. Otherwise, we already have metallic set to 0, so we don't need to set that again. It's not metallic, and the reflectance is going to be equal to specular.g directly. I have a complicated function here. You don't need to understand everything, but just the inputs and outputs mainly. The difference between this and what we've already been doing is we calculate a Fresnel reflectance is basically a substitute for KD and KS, the amount of light that is either diffuse or reflective. The difference is that it will change depending on the angle that you view the surface, and this can be calculated with our reflectance. Here's something you might not have known. Metal's entire color comes not from diffuse light, but from specular light. Because we don't have reflections yet, this will make the metal look mostly black. So let's comment this line out for now. You might be wondering what BRDF stands for. It's just a fancy name for what we were already doing. It's the bidirectional reflectance distribution function. Bidirectional because it involves the light and the view directions, two directions. Reflectance because this function involves the reflection of light, and it's a distribution function because it takes as an input all the light that hits the surface that you're looking at, and it sends as an output all the light that ends up bouncing towards you from that same surface. The falling diffuse is our diffuse light from before, the base color, now scaled by the Fresnel. Now we multiply n.L times the specular as well. We multiply the specular by the Fresnel reflectance as a substitute for Ks. We also use some really complex functions here, basically a way to take the same inputs and make them look a little nicer, a little closer to real life, using a bunch of math. So if we take this function, and we'll be replacing the diffuse and the specular with this, we'll need to put the light direction here, the view direction, the roughness, the normal in world space, the albedo. I think this is a good opportunity to rename our output color up here to albedo. The albedo is just the base color of the object before it has any lighting applied. That'll make more sense to have the albedo be the reflectance. Down here is where we will declare the output color. It used to be the albedo times the brightness, but now this term is not really the brightness. Really, this term is the output color. The base color of the object is now part of the BRDF. Let's make sure to multiply the base color by the ambient light, and now down here we can just multiply the whole thing by the light color, and make sure this is a vec3, and pass in metallic and reflectance. We no longer need this diffuse light calculation, and we no longer need this specular light calculation. There we go, and that's all we need to do. Well, we can see that something got messed up here. All we've got to do is remove this negative sign here because it doesn't apply here, and there we go. The difference is kind of subtle, but I think it looks a lot better, especially on shiny surfaces. You might have noticed that on the side of the block that does not face the sun, we don't see the normals or the specular or anything interesting, just the texture. The reason for that is we don't have a light direction for this part of the block because the sun is not influencing it. And if there's no light direction, there's no way for the normals to figure into the light calculation. There's a simple way that we can fix this. Instead of ambient light being a constant term, let's have ambient light also be a clamped dot product between an ambient light direction and the normal in world space. But how can there be an ambient light direction? Well, a good approximation of light coming from all different sides is the geonormal. So we can just create an ambient light direction and set it equal to the geonormal in world space. And we will still want to multiply this by 0.2 to make it dark since it's our ambient lighting. And look at that. Has a little bit of depth because the light is coming from a direction, so you can see the normals. This works for anything that's not in the path of the light. Now you probably have noticed that the sun has started looking pretty weird. The reason for that is those lighting calculations we've applied don't make sense to apply to the sun itself. So it's finally time we create another shader stage. To render the sun and the moon separately, we will create a gbuffers sky textured .vsh and .fsh. We'll have this be the same as the frag and vert shaders we already have, so let's copy and paste these, but we can skip all of the lighting calculations and simply output the albedo. Nice vanilla sun once again. We can simplify this further. All we need here is the text chord. Let's leave the foliage color in just in case. We don't need the light map, we don't need the view space position, we don't need geonormal, and we don't need the tangent. And we don't need the distant horizons blend for the sun, so we can go ahead and remove these from here. Remove those and remove those. Ah yes, not that one though. There we go. So why don't we go ahead and rename basic vert and basic frag to be lit vert and lit frag. We'll say OK so that automatically updates our include directives. Now we can create a basic vert.glsl and a basic frag.glsl. We can also delete this normal tangent function as well as all these uniforms we're not going to be using. There we go, much simpler. We can just take that and put that in our basic frag. Then we hash include basic frag.glsl. Do the same same thing here, but we'll include basic vert. Another thing we can delete here. We don't need VA UV2, and we don't need VA normal or VA tangent. Don't need the normal matrix. We're not using gbuffer model view inverse. And there we go. We're not using camera position. Let's take this, put it in our basic vert. Now let's do something even cooler and add shadows. Create a new file and name it shadow.vsh and another one that is shadow.fsh. These will run before everything else, and they'll render all geometry from the perspective of the sun. My apologies here because I accidentally forgot to record the part where I made the shadow shaders for the first time. I went back and re-recorded it. I also lost the part where I added Sky Basic and the line shaders. Fortunately, that's really easy to do. Once again, I copied and pasted from this wonderful template right here, base 330 for the Sky Basic shader, and for the gbuffer's line shader, I copied and pasted from this wonderful template right here, base 150, just to get this working just like it does on vanilla for both the vertex and the fragment shaders for both Sky Basic and gbuffer's line. So all you have to do is create the files and copy and paste the contents from the template. Once again, sorry about that. Lastly, I'll show you this part where I reorganize some files, and you can follow along. Just ignore the files that you don't have yet. And after that, we'll get back to shadows. Now to organizing. Let's create a folder called Programs. Make sure it's in Shaders. Whoops, I made a file called Programs. Okay, within Shaders, new folder, Programs. Let's take our GLSL files, move them in there. Start with just those two. Let VS Code do the refactoring so the includes are updated. Go ahead and move our lit GLSL in there too. Yes, please. The goal is to keep all of our actual code in Programs and to keep all of the base files outside. Since Line and Sky Basic is just code we got that replicates exactly what vanilla does, we'll leave them out here too. What we're going to do is copy and paste what's in the shadow files, put that in some GLSL files. Shadowfrag.glsl and shadowvert.glsl, just to keep things organized. Then we can hash include /programs/shadow_vert.glsl and do the same thing in FSH, but make it frag. Let's do the same thing for our distant horizons terrain files. vert.glsl, programs, not program. There we go. Do the same thing here, but frag, copy, and there we go. Now we have all our important files in this programs folder. And I wasn't recording when I filled out the shadow shaders, so let's get back to that. Luckily, the shadow stage is very simple. We can actually just take our basic vert and our basic frag, copy and paste those over to get started, and then we can remove everything we don't need. The main difference is that the shadow stage needs to use compatibility mode, at least in Iris. Let's write compatibility next to the version for the vertex and fragment shaders, and then this will be just like the distant horizons vertex shader. So we'll use F transform for GL position. We don't need that anymore. We will use GL color instead of VA color, and getting the texture coordinates will be just like getting the light map coordinates. In fact, we can copy and paste this to get started instead of VA UV0, and we also don't need VA position, and we don't need these matrices, and we don't need the chunk offset. It'll be the same texture matrix and multi-text chord variables, but it'll be 0 instead of 1, and that will actually be all that we need to do. Since the fragment stage can be exactly the same as the basic frag except for the version number, what we can go ahead and do is remove the version number from the basic frag, then write hash include basic frag. Then we're having some issues because there's no version number where we use this, which is gbuffer sky textured, so we can just go ahead and add the version for 60. You have to remember to include the folder it is in the include directive. Now, how do we get this shadow to actually appear? Let's go to our lit fragment shader, which is now starting to get kind of crowded. Gotta scroll for a long time to see anything. Let's go ahead and move the functions that we have here into their own file, functions.glsl. This will be our TBN normal tangent and our BRDF functions. Then right here, we will just hash include programs functions.glsl. You might have noticed the lighting section is getting kind of long. So let's make that into a function. Copy that, paste it in our functions folder. Let's make it return a vec3, which will be the output color. Let's call it lighting calculations. No inputs just yet. And let's make the brackets around the whole thing. At the end, we can say return output color. So right here, let's go ahead and say lighting calculations. We'll define vec3 output color equals lighting calculations. So we will have to pass in the albedo as an input. So let's go ahead and do that. Now this function should do everything we were doing, but now we just have a much shorter lighting section. And it still works. Look at that. First try. It's always nice. All right, now this is getting so big, we'll have to sort this into sections. Here we have the light direction. Here we have the normal calculations. You can go ahead and compress that a bit. Here we have material data, specular, metallic, reflectance, our if statements, roughness, and smoothness. Here we have our directions, and let's actually go ahead and move our shadow light direction down there. Our shadow light direction, our reflection of that shadow light direction, and the calculations we need for our view direction. Shininess, let's go ahead, move that to the material calculation section. This is the BRDF calculations. We got our ambient lighting. We got our combination of our ambient light with our BRDF. And then we got our light color. And this part will be our block lighting. Block and sky lighting. Our ambient and our BRDF. And our output. Wonderful. So let's go ahead and create a new section called shadow. In our lit frag, we just got to get a new uniform, which is shadow text 0 in our functions. So why don't we take a look at what is in shadow text 0. Use our texture coordinates and set this to shadow. Let's just look at RGB. And at the end here, let's just say output color equals shadow, just to see what's in there. Well, this doesn't seem right. We gotta remember the texture coordinates are not gonna let us actually view the texture, because the texture coordinates tell us where in the atlas of textures from the entire game is the texture for each object. So that's why we can still kind of see the world, even though this should be an image from the perspective of the sun. To fix this, let's use glfragchord.xy and divide it by vec2 view width, view height to get it into the correct range. Just for now, let's get those uniforms in that we need. View height and view width. And let's check out what this looks like. The reason that we only see this in the terrain is because this is the terrain shader that we're doing this in. But if we look down at the terrain, then we can really see the shadow map as it is. And doesn't that look crazy? I will do you the service of rotating it for you. But basically what we're seeing here is an orthographic perspective of the entire world from the perspective of the sun. Orthographic is real easy to show you with Blender. What the heck that even is, because they have a simple little toggle for it. So this is not orthographic, you know, it's got perspective, looks like a cube in 3D space. If we press this button, that is an orthographic perspective. The difference is that if I duplicate this cube here, a cube that is farther away will look exactly the same size as one that's close up, because there is no perspective distortion. All cubes look the same size because they are the same size. But when perspective is on, things that are closer up look much bigger than things that are farther away. You might be seeing, this is funny because I'm trying to do an example, but there's actually an illusion because these are all parallel lines and we're used to seeing things in perspective. There's an illusion, an optical illusion that this cube looks bigger than this one, but they are in fact the same size. Let me see if I can do a little graphic, cut this out and move it over there to show you they're the same size, but that's funny. Anyway, so this is the entire Minecraft world. You can see the seaweed down there at the bottom and the cave system and some trees. You can see it moves if our character flies up and drops down if our character drops down. And it kind of moves around with our character. So the reason that we have the entire world rendered from the perspective of the sun is so we can test whether something is in view of the sun. And if the sun can see it, we know light will hit it and it won't be in shadow. But if the sun cannot see it, light will not hit it, and it will be in shadow. So let's get to work on that. So where we actually want to access the shadow texture, it's not going to be at the texture coordinate or at the coordinate of the screen. We want to access it at the location of the fragment that we're looking at on the shadow map. You might have remembered seeing that glass wall on the shadow map. For the pixel on screen that renders that glass wall, we will want to check where that glass wall is on the shadow map. To do that, we're going to have to do some space conversion. So I'm actually going to create a new section called Space Conversion. What do you know? We already did some space conversion to get the view direction, so I'm going to move these up there to keep things organized. We're going to want the fragment in shadow screen space. Unfortunately, it's kind of a long path to get there, but we'll make it. Don't worry. So we will want the fragment in shadow screen space, and we will want the X and Y coordinates to access the proper location of the shadow texture. So let's define here the place we want to get the frag shadow screen space. And what do we have right now? We have the fragment in feet player space in world space. And look at that, we're already part of the way there. Now we just got to make it from feet player space all the way down here to shadow screen space. So let's follow the steps. We need the shadow model view matrix to get to shadow view space. So vec3 frag shadow view space equals shadow model view times the vector 4 of frag feet player space and 1.0, since it is a point in space. Of course, we will need to get the shadow model view matrix as a uniform. And I forgot, we got to convert the output, which is a vector 4, back into a vector 3. Now let's do project and divide shadow projection and shadow view position to get to shadow NDC position. Project and divide is a little function that's defined up here. I'm just going to use what's inside of it though, to keep things a little clearer. What we're basically going to do is go into what I'm going to call homogeneous space using the projection matrix, which in this case is shadow projection. So we will have vec4 homogeneous space equals shadow projection times vec4 position, which in this case is the shadow view position. Vector 4 frag homogeneous space, realize that equals the shadow projection matrix times the vector 4 of frag shadow view space and 1.0, no XYZ this time because we want a vector 4. Let's go ahead and define the shadow projection matrix, uniform mat4 shadow projection. Then to get to the next space, which is NDC space, that stands for normalized device coordinates. Basically, it ranges from -1 to 1, depending on which side of the screen it's on, no matter how big your screen size is. That's why it's normalized. We will do vector 3 frag NDC space equals frag homogeneous space dot XYZ over frag homogeneous space dot W. And that is still part of the project and divide matrix. Now we have shadow NDC space. We're nearly there. Oops, I forgot to say shadow NDC space. Next, we just gotta multiply by 0.5 and add 0.5. All this will do is change it from -1 to 1 to 0 to 1. So vec3, actually we don't need to define something new. This is what we're trying to get to. We're already there. That wasn't so bad, was it? So shadow screen space equals frag shadow NDC space times 0.5 plus 0.5. Now we have the fragment in shadow screen space. If we look at shadow now, we can really start to tell how shadows can come of this. Everything is colored based on how far away from the sun something is. Since we are accessing shadow text 0, if we look at how close to the sun this part of the floor is versus this part of the floor, this part of the floor looks darker because what the sun sees is this block and not this part of the floor. To get the shadow, now we can use the step function. For our first value here, we can just put frag shadow screen space dot z. Let's change this to a float and let's only access the R channel. That is where the depth is stored. The way step works is if the second value is greater than the first value, it returns 1. Otherwise, it returns 0. So if the depth as seen from the sun in frag shadow screen space is greater than the depth of the actual surface that we're looking at in frag shadow screen space. That means the sun cannot see this surface because something is in the way, something is closer. Therefore, that surface is in shadow. So let's take that shadow and multiply it by our BRDF. Go back to returning the output color. Okay, that doesn't quite look right. I'm not going to move around because that'll cause a lot of flickering, but there's a couple issues here. The first issue we can see is those weird wavy lines on the ground. That is called shadow acne. The reason that occurs is that our calculations of depth from the sun are not quite precise enough for it to exactly know whether this depth from the sun that we calculated from the fragment or the depth from the sun that we're calculating from shadow text 0 are closer. So it thinks it's both too close and far enough away, thinks it's shadowed and not in shadow, and it gets all fuzzy. All we need to do is add an offset. Instead of testing these values exactly, let's just move our fragment calculation just a little tiny bit farther away from the sun. Just extend the depth a little bit, and then there will only be shadow if the difference between these two values is greater than 0.001. Yay! That issue is gone, but now we have a new issue, which is that our shadow map is really low resolution. It's far too low of a resolution, and you can see that if you look at it really closely. We can increase it by using this built-in constant in the shadowfrag.glsl, and it's best to use a multiple of 2, so we can increase this to 8192 or something like that. I mean, that makes things better, but it's still far too low, and this will really hurt your performance, especially if you increase it even more than this. So what if we could use more resolution for shadows that are closer to us and less resolution for shadows that are farther from us? Well, we can start with the fact that our character is at the exact center of the shadow map in the shadow vertex stage. We could say that the vec2, since it's just a 2D map, distance from the player equals GL position.xy. The reason we can use GL position is because this is what tells the vertices of the entire world where they should go in the coordinate space that we're looking at all the fragments at, and the fragment shader just looks at those and writes them to the shadow map in that same space. So if we do something to move these vertices, we'll be distorting the shadow map. Now, if we want to use more space of the shadow map for things that are close by than for things that are far away, we can use this distance from player that we have to make it totally a distance, just a linear value. Instead of a vector 2 of xy distance, we can use the built-in length function. So given the x and the y coordinates, it'll just find the line that leads between those, from the origin where our player is standing to wherever this vertex is. Let's look at our shadow map again so we can see what we're doing. Let's use that glfragchord.xy over vec2 view width, view height again, .rgb. Now we can see the texture map again. One kind of simple way to do it would be to just zoom in, make everything bigger. Things close by are going to have more resolution. Of course, we'll lose entirely a lot of the things far away, but it's a good start. So let's take our GL position.xy, that's what we want to change, and let's divide it by 0.5 to make it bigger. Now we're zoomed in. That will work for things that are close up, but things that are far enough away now just will stop having shadow instantly. What if we divide by the distance from the player? Then when it's very small, this will be bigger. When it's very large, this will be smaller. Now we can't see anything. When distance from player is extremely small, this will just go to infinity, which is a little too much. The closest things to the player take up pretty much all of the shadow map, which is just far too much. So if we add 0.1 to this, just to make sure this doesn't get close to 0, look at that. It's a little hard to see, but you can see the big pillar there of wood that we have there. And way down there, you can see the distorted seaweed underwater and the caves. Things that are really far away take up much less space, and things that are close up take up a lot more space. All right, so we have our shadow map. If we go back to looking at the output color, things are not right for the shadow at all, and that's because since we did this distortion, we will need to do it when converting the fragment into the proper space as well. So right after NDC space. Let's find the distance from player of the NDC space, because that is the space where 0 is the center of the screen. And then we'll set NDC space dot XY. Then let's say vec3 distorted shadow NDC space. We're only distorting the X and the Y, so we're going to leave the Z the same, make that a vec3, and this will also be the frag shadow screen space dot XY. And then we have to remember to add the distorted into this last calculation here. Look at that, we did it. Nope, looks like there's a bit more shadow acne left here. A nice way, I think, to fix this, instead of doing the adjustment here, why don't we do the adjustment along the geonormal back when we're in feet player space? So let's make a vec3 adjusted feet player space equals frag feet player space plus 0.03 times the geonormal in world space. And then we need to make sure to use that instead for our shadow view space. There we go. All the shadow acne on the sides of blocks is gone. And we have shadows. Beautiful, beautiful shadows. And this works for everything, because the shadow pass renders everything in the entire world. So the sun can shadow everything. Now that we've got shadows working, I think it's a good time to take a little break from shadows, and let's make the block and sky lighting a little better. Right now we don't separate them, but if we did, things would be a little nicer. We wouldn't have to just multiply all of our lighting calculations by this light color, which isn't very realistic. Instead, we could use the ambient light value to be the block light, and then the block light would be directional, and we could use the skylight value to scale the light that comes from the sun. The first thing we're going to do is move this up here, delete this line, copy and paste this. All right, so one of these is going to be the block color. The other one is going to be the skylight. So how do we access just the block color? If we take a look at the light map itself, we can see that it ranges from the darkest values in the bottom left to the brightest values in the top right. The reason it goes from bottom left to top right, the X coordinate tells you the value of the block light color, and the Y coordinate tells you the value of the skylight color. So to separate the block light from the skylight, we need to zero out the other value. As you can see, the light map does not quite go to the edge of the screen. The reason for that is that there are only 32 fractional values that cover the light map along each axis, and they range from 1/32 to 31/32. So essentially the zero value for the light map is 1/32, not 0. So to access solely the block light, the X value, we will have to set 1/32 in the Y value. So for block light, we need the X value only, and the Y value will be 1/32.0. And let's make that a vector 2. Get the Y value of light map chords for the skylight. Make that a vector 2 and 1/32. Now they're separated, and let's name this the block light. Now instead of just a base 0.2 for the ambient light, let's multiply the ambient light by the block light plus the skylight. But since the main skylight is going to be coming from the BRDF, this is where we will put our 0.2. This skylight will be multiplied by 0.2 because it's going to be indirect light for surfaces that are not directly in view of the sun. Now that ambient light has a color component, let's make it a vector 3. And finally, let's multiply the skylight by the BRDF, which is all the surfaces that are directly in view of the sun. Change the output back to the output color, and there we go. Now our block lights have that same directional element that the ambient light, oh hello, that the ambient light has. Now our cave scenes should look better. All right, so we have shadows. Now why don't we add colored shadows? Shadow color 0 is the same as shadow text 0, except instead of the depth, it stores the color of every object that the sun hits. So if we just copy this texture part, change it to the color, then we are going to access the color of the first object that the sun hits. Let's make that RGB. Now we have shadow color. If instead of shadow, we multiply by shadow color, we can see what shadow color stores. Look at that. We do get beautiful colored shadows, but we also get very strange colored shadows for things that should not have colored shadows. Very, very strange. So all we need to do is use colored shadows for transparent objects and don't use colored shadows for non-transparent objects. To identify the difference, we can use another automatically generated texture, shadow text 1. This is the same as shadow text 0. It stores the depth from the perspective of the sun. The only difference is when it sees a transparent object, it will go right through it and hit the object behind it. So we can copy this line. Let's change this to is in shadow instead of just shadow. Let's change this one to is in non-colored shadow. And this will be shadow text 1. Everything else will stay the same. Now let's think about how we can combine these variables. So if the fragment is in shadow at all, then we check if it is in a non-colored shadow. If it is not in a non-colored shadow, so if it's in a colored shadow, we'll do something with shadow color. Right now, we're multiplying by is in shadow, which is 0 if there is shadow, and 1 if there is no shadow. So it reduces the light from the sun to 0 if there is shadow, and it keeps it the same by multiplying by 1 if there is no shadow. So what we can do is create a vec3 shadow multiplier, set it to a vector 3 of 1s initially for it to not be in shadow, so it won't change anything. And of course, these are floats that are 0 or 1, not booleans. So for our if statements, we have to say if is in shadow equals 1.0, and if is in non-colored shadow equals 1.0. So this statement will only trigger if the fragment is in a colored shadow. So then the shadow multiplier will be equal to the shadow color. So it will tint the sunlight by the shadow color. Otherwise, if it is in shadow, but it is not a colored shadow, then the shadow multiplier will be a vector 3 of zeros because there will be no light from the sun that gets through. Let's check out our results. Looks like we made a slight error there. Of course. So is in shadow is going to be 0, not 1 if it is in shadow, and is in non-colored shadow will also be 0. All right, let's see our results. There we go. We get colored shadows, and we can even overlap, and it will all work as expected. And we get non-colored shadows. Non-colored, color, though you can't really see. It's there, it's faint. Very, very beautiful. Non-colored shadows, and if we go to somewhere with stained glass, like this house, excuse me, Mr. Golem, look at that. Look at that, it's kind of faint, but it's there. You can see my shadow in it, yellow-colored shadow. We've got shadows. And that's all for this episode. Next episode will be all about reflections. We'll add reflections to metal and all shiny surfaces, as well as to all water, including distant horizons water. Thanks so much for watching. If you'd like to support my videos, check the link in the description and you can buy me a coffee. See you next time.